Hey, good morning again. So today for our CAP seminar, we have Dr. Alessandra Candian from the University of Amsterdam and the Leiden Observatory. And to introduce Alessandra, so Alessandra did her master in physics at Università degli Studi di Padova in Italy. And then she moved to the UK, where in 2012 she obtained her PhD in astrophysical chemistry at the University of Nottingham under the supervision of Peter Sarre. Then she did a short stay as a visiting researcher at the Instituto de Astrofísica de Andalucía, and in 2012 she moved to the Leiden Observatory in the Netherlands, first as a research associate in the group of Sander Tillens, and then she worked as an independent researcher supported by the Dutch Veni Fellowship. Then in 2019, she started working as a researcher at the Van Hoff Institute for Molecular Sciences of the University of Amsterdam, and she's still there. So I would like to say that Alessandra, she has applied for a Ramón y Cajal Fellowship this year, and also for one of these senior fellowships also offered by the Comunidad de Madrid here at CAP. So Alessandra, whenever you're ready, please.
Thank you very much, Izaskun, and good morning, everybody. I'm very happy to be here to give this seminar talking about stuff that I love, that is the aromatic universe. So during this seminar, I will try to bring you in a journey to show you how fascinating the world of carbonaceous molecule is. This is a short overview of my talk. So I will start with astrochemistry, so where we go from astrochemistry to PAS, some details about what we know about the population of astropaz, their photochemical evolution, and eventually beyond anharmonicity. So some of these words that I'm using here may be not familiar for you, but don't worry. I will, during the presentation, I will do my best to try to explain them. So one of the questions that made people in the universe, in our Earth at least, being very curious, is where we come from. Where the molecules and the atoms that built up our body or Earth come from. And a way to look at it is looking at the periodic table. This is a very specific periodic table of the elements, because for each of the elements, you see where they originate in the universe. And what is very clear from here is that we are made of stardust, as Carl Sagan, I think, said some times ago, because almost all the elements, except the very light one that have been created during the Big Bang, are coming from the nucleosynthesis inside stars. So the fact that there are stars, it's the condition that make us being there. And this is especially true for these 6 elements: carbon, nitrogen, oxygen, hydrogen, phosphorus, and sulfur. These elements for us are very important because they constitute up to 96% of the biomass of the Earth, and they are part of our body. They are part of the molecule that builds up our body. In particularly, carbon, nitrogen, and oxygen are the most abundant, among the most abundant in the universe, and they are seen everywhere. And this, it's like a smoking gun that tells us that if life exists somewhere else, and I believe it does, it have the same building block as the life that we know, the life that we see on Earth. So discipline was born something around 50 years ago, maybe even earlier, that is called astrochemistry. And the focus of astrochemistry is to understand how all the elements that we have seen from the periodic table, they can combine and form molecules in the very a typical condition that you can find in space. For example, very low temperature and very low densities. Astrochemistry not only want to understand how these molecules are created, but also how they evolve and how they end up being part of life on Earth, for example. And in that case, astrochemistry become, and let's say, moves to being astrobiology. As you can see from this plot, astrochemistry is built on three main pillars, which are experiments and theory. So experiments and theory that try to figure out the properties of these molecules. And then we have observation, astronomical observation, and modeling to try to understand the chemical evolution inside space. And these three pillars are in continuous feedback with one another. So astrochemistry is quite an interdisciplinary endeavor. Thanks to astrochemistry, we now know a lot more about the chemistry that happens in space. And now we can even use molecules as dyes. Astronomers can use molecules and detect them in places very far away from us, in faraway objects, and use them as a proxy for the physical condition that are present in these objects. For example, the temperature of the gas or the densities. The following question would be, but so are there many molecules outside there in space? And the reply is yes, there are. More than 220 molecules have been identified up to today. Every month a new molecule has been found in the pipeline or discovered by observations. So it's a very, we are seeing the science as we make it in some ways. And these molecules can be identified in different ways. For faraway objects, so objects that are in the interstellar medium, or even in nearby galaxies, we use remote techniques. For example, we detect molecules thanks to their vibrational spectrum or their rotational spectrum. As for the examples that I show on the top plots for C4H2 and formamide. If we wanted to understand the composition of molecules in a nearby object, and I'm talking planetary here, so for example, our solar system, we can use also in situ technique. And the one that is mostly used is mass spectrometry. And this technique, for example, has been used by in situ missions such as Huygens on Titan or Rosetta on Comet 67P to unveil the complexity of the chemistry that is taking place there. As you can see from the different peaks of carbonaceous molecule in Titan and the discovery of glycines on Comet 67P. One of the things that it's very interesting about this molecule that have been identified is that the large majority of them contain carbon. And why it is so? Because carbon is a shapeshifter, is a very interesting atom that is able to make bonds with itself and also with other molecules. And so we think it constitutes the building block of the origin for the life that we know. Among all these carbonaceous molecules that are present in space and in our solar system, I am particularly interested in polycyclic aromatic hydrocarbons. And you may say, poly what? Well, polycyclic aromatic hydrocarbons are molecules like the one that you can see on the top left side. I show 3 of them. They are made of carbon and hydrogen, hence the hydrocarbon name. And the carbons are connected in an honeycomb structure. And the hydrogens on the other side, they, let's say, decorate the edges of the molecule. Most of them are planar, but you can have also non-planar molecule. And because it's just a matter of combining hexagons, you can think there is a large there are a large number of isomers. The larger the number of hexagon that you can think, the larger the number of isomers. So now you get to the polycyclic, and aromatic is a very specific chemical properties that makes this molecule very much stable, and it doesn't have nothing to do with the aroma or the smell of it. On Earth, polycyclic aromatic hydrocarbons are everywhere. Indeed, they are the product of the incomplete combustion. So, for example, you can smell them and eat them in your barbecue. Because they are highly solubility in water, they are pollutant of water and also of air, because they are part of this particulate that is monitored constantly to understand how bad is the air we breathe in cities. And they have very bad characteristic, because some of them, the one that have a Bay region, so that have this kind of structure, not sure if you can see my pointer, are carcinogenic because they can link to the DNA, create a DNA adduct, and so they can, in that way, they become carcinogenic. So there is so much research on PAHs on Earth that there is a journal that deals with it. It's called Polycyclic Aromatic Compounds, and it comes out very, very often. Not only PAHs can be bad, but they also have a very interesting electronic application, because they have physical and optical properties that are different from other molecules. And so they have been researched for use in organic like emitted diodes, so OLED, in photovoltaics, so for harvesting energy from the sun, and also for terahertz sensors to use in the lab, in experiments, in many places. So these are the PAHs on Earth, but what about PAHs in space? Well, let's say that there is an almost universal agreement that polycyclic aromatic hydrocarbons are responsible of the aromatic infrared bands. The aromatic infrared bands, which are seen in this plot here, are a series of emission bands that are detected in different regions of our galaxy and also outside our galaxy. And these regions generally have a strong UV field, and there is presence of dust. These features, the strongest one happen at 3.3, 6.2, 7.7, 8.6, 11.2, and 12.7. And you see they are perched on top of the continuum that is created by the dust present in the same environment. There are other minor features, but the one that I mentioned before are the one that are mostly studied at this point. And how are PAHs related to this feature? So what happened is that the PAHs are free floating gas phase molecule in space. And when they absorb a UV photon, they become excited, and they use this excitation to vibrate, and this vibration release the energy and until they reach again the ground state. Of course, this vibration then gives rise to the aromatic infrared band spectrum. One of the things that is very characteristic of this kind of spectra is that this is a vibrational spectrum. So it's sensitive to particularly structure within, particularly motif within the structure of the molecule, and not sensitive to a specific molecule. Hence, we cannot really use at this point the aromatic infrared bands to really pinpoint which exact PAH is out there. Still, we can do a lot of science with that. For example, because we see these aromatic infrared bands wherever there is an estimation that PAHs that produce these aromatic infrared bands contains up to 20% of all the carbon in the universe. The emission from the PAHs, it's very strong and comes, as I say, from everywhere. Here I show you on the bottom left side an image of M81, so a spiral galaxy very similar to our Milky Way that is detected by Spitzer in the filter of one of the PAH emission band. All the red that you see is PAH. It's a lot, huh? If you zoom in one of the star-forming region, and you see, for example, on top you have the pillar of creation, again with the Spitzer PAH filter, everything in red is illuminated bar. Even protoplanetary disks that you can find this star-forming region have emission from PAS. So PAS, the emission from PAS is strong and is ubiquitous. It starts very early in the universe. We have detection of pi emission up to a redshift equal 4. And they go all through the cycle of the galaxy till we reach a planetary system. Because indeed, PAS have also been detected abundantly in meteorites. They are present in comets and in interstellar dust particles. And also they are abundant in the atmosphere of Titan, very close by. So what do we know about PAS? Here I'll just try to make an overview. Of course, if you want to have more information, there are 2 reviews that you can look up and by Tillens 2008 and 2013. So we think that PAS are originated in the outflows of a Volvo star that are carbon rich. That's the general idea, and the type of chemistry that happens there, it's high density, high temperatures, is a combustion chemistry, the same one that we see pretty much when we do a barbecue. But recently there are indications that that may not be, this can be a very simplistic view of seeing things. So there is currently a lot of effort from the Nanocosmos project into understanding better where the carbonaceous material come from and how it ends up there. So once this carbonaceous material is formed, it ends up in the interstellar medium. And there the PAS are a very important ingredient because they are needed to measure or model the extinction curve. That is this curve that gives you an idea of how much dust and material there is between you and an object that you see in your sightline. PAS have been proposed as a surface where you can form molecular hydrogen in environments where dust, so larger dust, is not abundant. And also PAS regulate the temperature of the gas of the interstellar medium and the charge balance through the photoelectric effect. And as such, they have an important role in shaping the star formation in galaxy. And it comes to no surprise that there is a correlation that is seen in this plot here between the luminosity of PAS in galaxies and their star formation rate. So what do we know about the population of Astro-PA? We say that we cannot really pinpoint which specific PA is there, but we can have ideas about subclasses. And what is great is that in the past 2 generations of satellite, ISO and Spitzer, started to give an idea of how the IB, so the aromatic infrared band spectrum, changes. It seems remarkably similar, but then when you go and look at the details, you see variation in the peak position of the bands, in the bandwidth, and also in the relative intensity between the bands. Here, as an example, I show you the red rectangle. It is one of my favorite objects. It's an evolved star that is a carbon rich. And if you put the, you observe 3 different positions on the star, which is in the center and across the nebula, and you record the PA emission, you see that there is a clear variation in the profile of the band. And this is seen not only within an object, but also among different objects. Here is a compilation of different spectra of objects from our Milky Way, except the orange one, which is from the Small Magellanic Cloud, where the PA spectrum has been detected, and where variation are seen across different levels. So much that people have proposed a classification. So they classify these spectra based on their properties, and they realize that there is some kind of an evolution, and these variations are telling us a lot about the subclasses of the PAHs that are responsible for this spectrum. And these PAHs, these subclasses are clearly responding to the specific physical and chemical condition in the different objects, and these shape the population. So thanks to a lot of work for many different people, we now have a better understanding of the population of Astropa. Here I just put a very incomplete biography. There are a lot of work outside there, but what I wanted to highlight here, and it is very important, that again, all this work has been a continuous feedback between theory and experiment, modeling and observation. Without that, we wouldn't know so much about the Astropa population. So here are some examples of what we know of this population. We know that the PAs can be charged in space, have a different charge. We know that they can have a specific size that is larger than 40 carbon atoms. They can have heteroatom substitution. That is when an atom within the molecule is substituted by another. For example, you can substitute a carbon with a nitrogen or a hydrogen with a deuterium. They can have a functional group, like methyl or hydroxy group that decorates the boundaries of the molecule. And there may be different members. Now, I'm going to give you some examples of how we came to understand this. So, for example, for charge, it was thanks to experiment on neutral and charged PAHs that we realized that their infrared spectrum is quite different. Neutral PA tend to have stronger features around 3 micron, as you see from the top trace on the experimental plot here, and at longer wavelength, so 10 to 15 micron. Charged PAs, on the other side, are a stronger feature in the middle, between 6 and 9 micron. Thanks to this insight from the experiment, we were able to use estimate PA spectrum in their neutral and charged space to highlight their position in a spectroscopic map that were obtained, for example, by Spitzer. An example is shown here on the bottom. So on the left-hand side, you see the signal of what are considered charged PAs in a data cube from an extragalactic object, the reflection nebula. And on the right-hand side, you see where the neutral PAs are. For reference, in this nebula, in this reflection nebula, the star is at around 25.0 in the unit of the spectrum. We also know that PA have a specific size and they should be larger than 40 carbon atoms. And how do we know that? Because thanks to theory and again experiments, we know that if we take the ratio of the band happening at 3.3 micron and the one at 11.2, this is a proxy, a very good proxy for size. And making observation with SOFIA, we were able for the first time to map the spatial distribution of different size of PAHs in the reflection nebula, NGC 7023. So the colors that you see here refers directly to, that you see in the astronomical map, refers directly to the colors that you see in the plot below. So where you see red, you have small PAs, and when you see darker color like blue and purple, you have larger PAs. And again, the determination tells us that in this specific region, PAs happen between 50 and 120 carbon atom. Their size is around that. Another thing that we know is that the PA can be substituted. And back in 2016, with Kirsten Donnie, a master student, we find evidence for the presence of PA containing deuterium. So PA molecules where the hydrogen is substituted with deuterium. When you have a CD bond instead of CH, you have a shift in the position where the vibrational mode happens, and it should happen around 4.4 and 4.7. So here you see the small features of the deuterated PAs. And this was very exciting. It was thought and it was very exciting because deuterium is together with the hydrogen element that has been created during the Big Bang. And so what we detect now, the abundance of deuterium that we detect out in the interstellar medium is just the witness of all the processing of the interstellar medium and the consummation of the gas to create stars. And locally, we see a large fluctuation of in the interstellar medium. And now we think that Pa can be some of the reason of it, that some of these can be incorporated into PAS. And another thing that we look at is members. As I say, we cannot identify members, but there are some specific molecules that can be identified only also thanks to their vibrational spectrum. And an example is C60, fullerene. So C60 is the largest molecule that has been detected in space. It has been detected for the first time in 2010 in a planetary nebula by Yankami, but since then it has been detected in many different regions within our Milky Way and also in the Magellanic Cloud. Even if it doesn't have hydrogens, because it's just a full carbon molecule, C60 is also aromatic. And here in the plot, you can see the vibration of C60 in purple and of C70, so the larger version, in blue. Highlighted in the Spitzer spectrum that is in white of the planetary nebula TC1. More recently, C60 has been detected also in its ionized state, so as a cation, in the UV visible. And this was a huge breakthrough because it involved the diffuse interstellar band. So just to explain, so these are the two bands that have been ascribed to C60 plus. And the diffuse interstellar bands, for who of you who do not know, it's called the longest standing problem in molecular spectroscopy, in astronomical molecular spectroscopy. This is a series of a family of absorption band that happens between the near UV to the near infrared. Here you see a sample of those, and they are detected toward the diffuse medium. And we don't know what causes them. So the fact that now we know that here that only the two strongest ones are seen are due to C60 plus is a huge step forward in understanding part of the molecular inventory in the diffuse interstellar medium. Actually, because Pa are so abundant and widespread, there are people are pushing forward the idea that some of these dips are also due to PAS. So they are the visible and the visible transitions of PAS that absorb those photons that then they used to re-emit somewhere else. But the problem here is that to be able to identify and have a very strong identification, you need very high resolution astronomical spectra, which are quite difficult to obtain, and you need to have also a very high resolution UV visible spectroscopy of these specific species, and in conditions that are relevant, so they need to be in the gas phase and cold. So this experiment like that were conducted for C60 plus and led to the identification of these species. More recently, we had also a new very exciting discovery, because on the radio side, so using radio astronomy, the first Pa molecules have been detected. So this Pa molecule is cyanonaphthalene, so it's a two-ring naphthalene, which is connected to a CN group. And these two molecules have been detected by Brett McGuire and his collaborators in the Taurus molecular cloud. I think the paper came out less than a month ago. Previously, in the same cloud, benzonitrile, which is the benzene ring with a CN group, was detected, and that place seems to be a very trove of treasures with respect of carbonaceous molecule. This detection is very exciting because it's opening up a lot of questions for which we don't know the answer, and we hope to be able to solve in the nearby future. For example, how these molecules ended up there. Are they just what is left from the past that have been created in the evolved star and have been the interstellar medium, or are there reactions that can create this molecule even in the very cold temperature of this molecular cloud, which I think it's around 10K. Well, it's all very exciting, and we hope that soon more information will be available to understand better. So I think I kind of convinced you that we have a population of large organic out there, and all these changes and interplaces between the charge, the size, and the substitution is telling us that active chemistry is taking place, molded by the physical condition in different environments. And this active chemistry shape the population of large PAS and organics. And to understand this, we need experiment, we need quantum chemistry calculation, we need modeling and observation all together to be able to make sense of what we see. And to give you some example of what of the type of work that can be done to this respect, I want to show you something about the photochemical evolution of PAS. So try to understand how PAS can evolve thanks to the interaction with the photons in interstellar region. So here on the left-hand side, I show you composite images of a very famous object, which is NGC 7023. I already showed it several times during this talk. This is a very well-known reflection nebula. The nebula you see as it's within this square, and the star is this blue dot with that is assigned by the arrow. If you do a zoom up there and you look at the emission due by dust in red, PAHs in green, and PAHs in green and C60, so fullerene in blue, you see a very clear stratification. You see that the red dominated further away from the star, where the condition of the gas is dense enough for not many UV photons to penetrate there. In those regions, we believe that a population of very small grains exist, and possible candidates for these very small grains are clusters of PA, which means these are PAs that are clustered one atop of the other, and they're kept together by van der Waals forces. As soon as the UV photons is able to penetrate these layers, these photons give enough energy to overcome these van der Waals forces, and then you start to have standard PA, like the one that I show you here on top, and their presence dominate here where the green is. But as soon as we get closer to the star, we have even more flux from UV photons, and these PA are photodissociated. So they start to lose their hydrogen, they change their shape, and they end up being C60. And this was an idea that, based on this observation, was put forward by Bernet and Tillens, and then was later confirmed by a lab experiment where at least the second part, so the evolution from PAS to C60, in the experiment they took one of these PAS, actually specifically this one, and they irradiated. And what they noticed is that the hydrogen were being removed, the C2 were removed, and then the mass spectrum of C60 was coming up. So this was a very good evidence that if you have a large enough PA, can lead to the formation of C60 ring. Okay, so we have the observation, we have the experiment, but how can we model that? Well, that's not easy, because paths, as I was saying at the beginning, come in many different forms, in many different isomeric form, in different charges. And so it's quite a challenge to be able to understand the evolution of a complex picture like the one that I show you here. So this is what we think is happening in the PDR, so the photo dissociation region that I showed you earlier, NGC 7023. You start in the molecular crowd with these grains, very small grains. You, as soon as the UV field becomes stronger, you start to break down the van der Waals forces, and so you have the small paths. And then as the UV becomes stronger and stronger as you get closer to the star that is on the left-hand side, the small paths that are less stable get destroyed. You end up with a largest path that can become even ionized or doubly positively ionized, and you end up with fullerene. So here there are many different mechanisms that are at play. You have hydrogenation, so you can have that the hydrogen gas that is around interact with these PAHs, creating superhydrogenated path. You can have isomerization, so the absorption of the photon can change the shape of the molecule without breaking it out, and you can have dehydrogenation and destruction. So one of the things that you can do is to try to model the very basics of all these complex photochemical modeling. For example, try to understand how the hydrogen coverage and the charge of specific path changes within the condition of these PDR regions. And so several path kinetic models exist. And what you need to do is, of course, you need to start with, you cannot use all your paths. So in the model that we developed with Heather Hendricks, we use coronin, which is the molecule that is vibrating in the slide here, and then a slightly larger version, which is circumcoronin and circumcoronin. So we use 3 molecules with size between 24 and 96 carbon atoms. We consider that they could be anions, neutral or cations, and they can acquire up to 2 additional hydrogen atoms thanks to the interaction with the hydrogen gas present in the region. For the path kinetic model, we have considered multi-photon dissociation events. And this is because the larger that you go with paths, the more stable they become. So in order to be able to dissociate, they need to absorb several photons. Otherwise, nothing will happen. They will very quickly and very effectively release their excessive power vibrating, for example, and creating the IVs. And to make these kinetic molecules, we use real properties of the molecule. So the for example, the actual value for the bond, the energy that you need to remove an hydrogen from the bond, or reaction rate that were taken from the experiments. Among the reactions that we consider, we use a recombination and attachment with electrons, hydrogen and molecular hydrogen photodissociation, hydrogen addition, and molecular hydrogen abstraction. This is the result of the modeling. So here you are seeing on the y-axis of the 2 plots the G0, which is a measure of the intensity of the radiation field, and on the x-axis you have NH, or the density of the medium. The oval on the top are the conditions that typically you find in a standard PDR, photodissociation region, and while the oval at the bottom is the condition found in the diffuse interstellar medium. So what we see is that for carbons that are, for paths that are smaller than 54 carbon atoms, those are completely dehydrogenated, and this is seen here with the word cluster. So here I'm talking about carbon cluster in this pink region on the top left corner. Then you have that molecules between 50 and 96. So these two bonds can be found normally hydrogenated in many environments, but only and they can also find in super hydrogenated form, so they can acquire additional hydrogen in some specific environment depending on their size. Together with this, we also look at the contribution of PA to the molecular hydrogen formation. And based on this model, we predict a maximum of 1%. That is not very much. But the more we dive into the real molecular properties of these PAs, the more we understand how they behave, the better we are able to model their behavior also in the interstellar medium. And for example, if you consider that PAs, the hydrogen of PAs do not always stay like that, but they can roam, if they have some energy, they can roam around the surface of the molecule, and they can end up in a position where two hydrogen atoms are attached to the same carbon, and from here they can be released as molecular hydrogen. If you consider this possibility, you can reconsider your efficiency for molecular hydrogen formation, and this goes up to 10%. And for final, let's see how much time I have. Okay, I'll try to be quick. So the final thing I want to briefly talk about is the harmonic approximation. So the large majority of the infrared spectra that we evaluate, that we calculate with quantum chemistry techniques for these PAs, and they're very important to figure out their properties, comparing with observations, are done in the harmonic approximation. So thinking that it doesn't matter how much energy there is in the bond, you can stretch it, but it will never break. But of course, this is not true. And it is even less true when we consider PAHs, because they are, once they absorb their UV photon, they are highly excited, highly vibrationally excited. At this point, we decided to investigate the we decided to investigate how we can evaluate the real, so the anharmonic spectrum of PAHs. And we did it using the second order vibrational perturbation theory. I wouldn't go much into details. You can even look at these two papers for a very detailed description of the theory behind it. But the idea is that you take the potential energy surface of your specific molecule, your n-dimensional potential energy surface, and you use a tailored extension to be able to model it better. And thanks using that, you can obtain the anharmonic infrared spectrum of PAHs. So we did it. We together with Cameron Mackey, we pioneered calculation of the anharmonic spectrum of all these molecules. And you may ask, okay, but why only this? Why you didn't do the large one that you told me are in space with 40 carbon atoms? Well, this method is very computationally expensive. If I wanted the harmonic spectrum, so the standard spectrum of this tiny molecule here on top, naphthalene, I need, I don't know, 15 minutes on 8 cores. But if I wanted the anharmonic spectrum on 8 cores, it needs 1 day and a half. And this grows, and the time that you need grows with the power of 3 of the number of electrons. So very quickly you reach things that you cannot really calculate in your lifetime. So we calculate the spectrum and we compare to the experiment. We built up a very nice collaboration with people at the University of Amsterdam, where then they did for us high resolution vibrational experiments in the condition of PAS in the interstellar medium. So we are sure that we have very cold PAS, maximum 30K, and they are isomer selected. So we really know that we are looking at that PA. Here I want to show you how we fare with the theory. So on this is the experiment for a specific PA, the hydrophenantry. The experiment is on the bottom, and this is the harmonic spectrum, how the harmonic spectrum looks like. You see, for the first plot, the 3 micron region, you have some bands that are, I mean, it's okay. But for the 5 micron region, there is nothing. There are no prediction there. But if we go with our calculation, the enharmonic spectrum, well, it's quite a thing. The comparison between the theory and the experiment, it's very good. We have an average deviation at this at cold temperature of 0 plus or minus 0.17% in the position of the in the positions of the peak. And this is quite exciting because it means that now we have a theoretical tool that can give us the real spectrum of a PA, even though you cannot detect, even if you cannot detect that spectrum in the lab, if you have technical if you have technical issues. So the idea is that now that you know how really a molecule vibrates, simulate also its emission spectrum in space. Because the emission that we see of PAS, it's due to of this process of infrared cascading, so the vibrational emission that led the molecule to relax. And we need to model that in order to be able to compare with the observation. And the reply is, yes, we can. So here I show you the change in the position and bandwidth of a specific mode for the molecule anthracene, following the absorption of photons of different energies. And in blue, and in black, you have the total cascade, considering a black body distribution for a source. What is very nice is that you can predict this very nicely, this very steep left side of the feature and the tail that goes at a longer wavelength, very similarly to what we see in astronomical environment. I show you here on the right-hand side the spectrum of the same real astronomical feature in the Orion bar. So this is really quite promising. And the idea is that if we use a sample of an harmonic spectra, we can predict. We are starting to get very close to be able to predict how these paths will meet in space. And for example, I challenge you, which one here is the spectrum that comes from space, so the observation, and which one is the one that we model using our anharmonic calculations and the emission model? Well, it's the one on the top, if you want to know. Our model is the one on the top. So these new tools that we are developing is really is going to become a great tool, because it will allow everybody that has PA feature in their spectrum to be able to model them and to understand better the population of PAs there. So we have a very exciting future in front of us, because we have theoretical and experimental techniques that are becoming available. Of course, I'm more on the theoretical side, so that's where that was the focus of my talk in this step. And as I think many of you at CAB know, we have the new observation that will be brought by the James Webb Space Telescope. And funny enough, James Webb Space Telescope is the PA machine. It has the same shape of circumcoronin. We have early release science program that has been accepted. PIs Olivier Bernet, Emilie Abarth, and A. Peters, that is going really to look with extremely high spatial and spectral resolution to these photodissociation regions. And it will be able to, we will be able to get beautiful PA spectra and be able to understand better their photochemical evolution there. So I think that for now I'll stop here. I can go on for long, but it's already late. Here I put the slide with all the collaborators that I had along the year and the source of funding. And in particular, I would like to acknowledge all the students that are highlighted in orange, that with their inspiration, and their new ideas helped me push forward a little bit what we were doing. And of course, I would like to thank you for your attention, and I will reply to any question you have. Thank you very much.
Thank you, Alessandra. Thank you very much for this great talk. So we already have a question in the chat. So this is from Laura Colsi. She asks, she says, very interesting talk. Is there an estimation of the percentage of nitrogen substituted PAS with respect to the normal PAS?
Oh yes, sorry. There is a many studies have been done to try to understand how much nitrogen there is in PAS. The reply is not easy because there is only one band that is very likely connected to nitrogenated PAS, at least in the interstellar medium. And I was, sorry, I will show you the slide, 1 second. So where is it? Well, I cannot find it anymore. Oh, no, there it is. So we believe that the 6.2 micron feature, that is one of the strongest and is seen even in galaxies, is due to nitrogenated PAS. But there are some problems there because we know that putting nitrogen in PAS make them more less strong, less stable. So I think that, to far of my knowledge, there is not a this part has not been studied in details, but you know what is important is that you can have a lot of these carbon and nitrogen compound in more quiescent region, for example, in those molecular clouds where benzonitrile has been found. So yeah, that could be, I think that the reply to the question is, I think so.
And there's a follow-up question from Laura as well. And then she asks, could this nitrogen end to be part of the combs formed on grains in the star-forming regions, in particular in a top-down approach?
The top-down approach. Well, I think there is the science of comms lately. It's very every day I see new papers with new ideas on how comms can be formed both in the gas phase and in the grain. For sure, if this kind of paths are out there, they would be embedded in grains. So why not? I'm not a solid state chemist, so I wouldn't know the details, but I think it's quite possible.
Mm-hmm. Okay, are there any other questions? Let's see if there are any hands raising, or if you have any other questions, you can also type them in the chat. In the meantime, then I actually have a related question. So because we've seen these detections of cyanonaphthalene from McGuire in TMC1.
Yeah.
Because in this reflection nebula, basically what you were saying is that you start with these very small grains and then they are photo-dissociated. So you go from a top-down approach. But then for TMC1, what is your feeling for what's happening for the formation of these paths in there? Do you think it's the same top-down approach, or do you think these molecules start by being very small and then they can grow through gas phase reactions? What is your feeling?
Well, my feeling is that there are roots in the gas phase that can create this molecule from smaller one up. I think because in the paper where they have the detection of cyanonaphthalene, they did a chemical modeling trying to figure out. Based on the current knowledge of formation route for these specific molecules, to figure out if it could be created there. And even if they think that all, I don't know which huge percentage of carbon is locked in naphthalene, they cannot reproduce the abundance that have been found there. So for me, that's a very strong, let's say, it's a very strong proof that we need also the cold roots, so the bottom-up roots for that.
Yeah. Okay. Okay, we have another question in the chat from Victor Rivilla. Since the simplest paths have been detected in the... so it's the same.
It's exactly the same question.
Exactly the same question. Sorry, I hadn't read it. So there's another question by Giacomo Mulas. So you can speak.
Hi, Alessandra. Can you hear me?
Okay. Yes, I can. Ciao, Giacomo.
Okay. Ciao. I have a question about the last part of your talk. Very impressive modeling of the band shapes. I have one curiosity because earlier in your talk, you said that the problem is in trying to apply this to large species. But then you do it to interpret observations in which we have been thinking so far, at least, that molecules larger than 40 carbon atoms are present. And you can't do them anharmonic so far because they are too big. So how do you bridge this gap?
Well, I can see two different ways of doing it. The first one that has been, I think you also, the one that you use in one of your latest paper is to try to use molecular dynamic simulation, because you can take out, you can convert the result of your molecular dynamic simulation into an harmonic spectrum. And in that case, the anharmonicity is already part of the scheme that you use to run this molecular dynamic simulation, being DFT, ab initio, whatever. And that, I think, it's a strong potential. Another thing that I'm thinking and I'm trying to explore is to try to use machine learning, because I have this idea that all these vibrations and all these combination bands are specific combination band between modes, and these modes are related to the shape of your molecule. So I'm wondering if based on the database that we have, we can figure out a way to, take out some recipes that tells you, okay, if you have this specific subshape of your PAHs, then these modes are active, and then this, how they would affect your anharmonic spectrum. But yeah, this is at the moment it's something I'm looking into it, but I don't have much to show yet, unfortunately.
Can I just ask a very short follow-up question? Sure. About the accuracy that you achieve with the anharmonic calculations. We both know that one of the crucial points with that is choosing the appropriate or the most lucky, if you want, functionals and basis set couple. So what have you been using lately? Because I have seen that in some of your paper you used BISRELIP with the magic N0 whatever Baroness.
070.
But in some other tests, it appears that the older version B97.1 with TZ2P is even more accurate still. So what is the...
what is, yeah, that's one of the things that I before to go more into the expanding to larger paths, I'd really like to do a stronger benchmark of the theory, because at that point, also given the computational time needed to do this, you really need to try and several basis set and functional. We know that the BISRELIP N07D has an advantage that is faster for the way the basis set description is implemented. It goes very well with Gaussian, but it has issues not only when you have methyl group, which is we know the problems that methyl group create in anharmonic spectra, but also depending on the size. We have a lot of imaginary modes coming out that we don't really understand, or positive correction. B971 and TZ2P, which was the earlier theory method that we use, was giving good results, but the amount of positive correction that we start to add when we move to 3-ring PAHs start to become larger. So we had to make ad hoc simplification of our scheme, and we didn't like that because, you know, ad hoc, you know, we really want to understand why it is so. So that's why I think, you know, I tend to give very long replies, but that's why I think a solid benchmark is what we really need to do next.
Thank you.
Thank you.
Are there any other questions? I have a curiosity. So I was wondering, you mentioned at the beginning also the detection of these paths in planetary body, no, in Titan, for example. So can any of these calculations be used for the detection of these paths in these moons?
Well, yeah, so their paths in Titans have been detected with the mass spectrum, so we just know their size. But we don't know exactly their composition. The detection with spectroscopy, it's difficult because you need to excite them. You need to have UV emission to excite them. And I think the only paper that is out by Lopez Puerta, it's on a specific set of Cassini spectra in a moment where Titan was irradiated by the sun. So you were able to have a 3-micron feature, let's say, hidden by the CEH4 huge transition. But then the spectrometer stopped there at that altitude in the atmosphere, so we don't know much more. What we can do definitely is to try to figure out how you can evolve from the mass that we see in the mass spectrum to the larger paths that are seen deeper down in the atmosphere. Though that's definitely can be done. And of course, you know, in 2030, I think there is the Dragonfly mission, which is the new, this crazy drone that is going to go to Titan and try to understand better the atmosphere. So I think there is a lot of preparation going on for that mission. And yeah, I hope that to be able to participate to that.
Great, thank you. Thanks so much. Okay, so if there are no other questions, then thank you very much, Alessandra, for the
thank you
today.
everybody.
And thank you, everybody. I'm going to stop recording now.